Good afternoon, everyone. My name is Cassidy Harridan, and today I'll be presenting on using automated core imaging technology, specifically looking at opportunities for integrating hyperspectral mineralogy with structural orientation data to produce more robust structural interpretations. My co-authors are Laurel Stothers and Carrie Dial-Wurst, and we're with Corescan. I think everyone in this session can appreciate the importance of structural assessment as it applies to ore deposits. The structural complexity of ore deposits may vary depending on the ore deposit type we're looking at, but being able to measure structures and using that information remains absolutely fundamental to characterizing and understanding most of the ore bodies that we work in. In exploration, we use structural data to map vein density and distribution, to understand fluid pathways and paragenesis, as well as to assess controls on mineralization and deposit geometry. In mining, we use structural data to predict geotechnical behavior of an ore body, and this helps us with our mine planning decisions, as well as understanding the economics of ore recovery, which is really important. On the right-hand side of this slide is an example from Benedicto et al. From a paper earlier this year, where they used acoustic televiewer data, which is a downhole in situ method of structural data collection, to interpret a complex structurally controlled uranium deposit in the Athabasca Basin here in Canada. And what they found is that there was a slight difference in the mineralized versus non-mineralized structures, and this in the orientation of those. And this helped them in both updating their geology model and understanding the geology, as well as the regional paragenesis. So this is a really fantastic example of how integrating not just the orientations of our structures, but adding the component of mineralogy gives us more information and more robust models for the ore deposits that we're working in. Now, acoustic televiewer is one method of collecting structural data, but a lot of the structural data that we use actually comes from logging of drill core. And traditionally, we collect structural data using manual methods. When we're talking about collecting orientation data, this includes measuring alpha and beta angles of our planes and gamma angles of our lines using manual tools such as rulers and wraparound protractors. More recent tools have been developed to help speed up the data collection process. One example is the IQ logger here in the center of the slide, but this is still a manual measurement. So someone still has to go through the core and highlight those structures and actually measure them using this digital tool. Determining mineralogy when we're manually logging is typically done by visual inspection and looking at the mineralogy that's in the structures and around the structures. And this can be particularly challenging in hydrothermal ore deposits because our hydrothermal minerals, especially if we're talking about phyllosilicates, can be very fine-grained. They obviously don't have a lot of different color changes that are obvious to the human eye. And so as an example, on the right-hand side of this slide, here's a section of core where we see visually there's not much change in the color, grain size, texture, anything like that. But if we actually look at the hyperspectral mineralogy, which is what these colored maps are, we can see that this section shows us kaolinite at the top, porphyllite in the center near the structure, moving into montmorillonite. And those are three minerals that from an exploration perspective are very different. They have very different implications for paragenesis and the evolution of the hydrothermal fluids. And from a mining perspective, these are three minerals with very different processing behaviors. So knowing that those minerals are present in that section is very important and very difficult to determine visually. Now, what are some opportunities for automating the actual structural data collection component of our process? Well, we know that we can apply and successfully apply manually collected data to exploration and mining. The people that do this are very good. The geotechnical engineers, the geologists that collect this data are very good at what they do, and we can build mines on that data. But the truth is that this process, when we do it manually, is very labor intensive. It's very time consuming. It's difficult to find enough time to leave core on a bench for as long as it requires to actually be logged in great detail. And so this can lead to either incomplete data sets or inconsistent data sets that we're using for our modeling. Using automated core imaging technology allows us to collect high volumes of consistent drill core information from multiple co-registered sensors. And this includes things like high resolution core photography, geochemical data. Some of these systems actually have XRF sensors and other geochemical sensors on board, and mineralogical data. So in the case of Corescan, we collect reflectance hyperspectral mineralogy in an imaging sense on the surface of our drill core. When we compare the automated methods to the manual data collection methods, the automated methods increase not only the speed and efficiency with which we're able to collect this data, but also the density of structural measurements that we can collect downhole. And that's absolutely key, getting a lot of information rapidly and consistently. So how do we actually automate the structural detection and measurement? Well, first we need to be able to actually find the structures in these images. And we can do that. We do that at Corescan using a combination of high resolution 3D profiler data as well as core imagery. That 3D profiler data is essentially a three-dimensional surface topography measurement of the surface of our core, very similar to a digital elevation model that you would use in GIS software. And so with these two base data sets, we actually run a series of contouring and gradient calculations, segmentation and morphological filtering steps, and finally some adaptive feature thresholding methods that allow us to actually extract and orient the structures that are observed in the image. And if you want to learn more about that adaptive feature thresholding method, please check out Laurel Stother's Speed Talk ST055 in the Beyond 2020 session, where she actually looks at the details of improving our measurement of structural orientations using these adaptive feature methods. But what I want to talk about today is how we can integrate the hyperspectral mineralogy once we know where those structures are in the image and what their orientations are. So once we've oriented them, we can actually look at interrogating the hyperspectral mineralogy because all this information is co-registered, right? So we have mineralogy that's co-registered with the location of the structures. And we do that through three primary steps. The first is to actually define the spatial extents of the structural features that have been identified in the image. So in that center panel with the white pixels, you'll see this defines the extent of the structure that's been identified in this image. The next step is to apply a series of multiple distance buffers, both within and around the defined structural feature. So, and this is at user-defined intervals. So in the example, you can see we have light purple pixels that represents the extent of the structure. We have darker purple pixels, and this represents a 5mm buffer moving away from the structure that's been identified. These can be set to any interval that's required for the data interrogation task at hand. So anywhere from 5mm, or if we need to know what's happening 100mm, 200mm away, we can interrogate all that automatically within the software using any user-defined threshold. We then query the co-registered hyperspectral mineralogy image within those buffered distances. And what comes out of that is a report of the mineralogy both within the structure that we've defined and all of the buffered distances that we've set up. So what are the opportunities for integrating this? Well, once we know the structural orientations, which we've automatically pulled out of the data, we can then interrogate the hyperspectral mineralogical data, put these two data sets together. And what this allows us to do is delineate sets of structures, whether that be fractures, veins, joints, even in deposits where we have seemingly uniform orientations. So here's an example of that at the bottom of the screen. We have a rose diagram that's showing the open joint orientations from an orogenic gold deposit. And if we're to look at that, we see that primarily we have sort of a southeast trend to all of our structures with not much else going on. But on the right-hand side of the slide, what we've done is we've actually colored that rose diagram based on the primary mineralogy within the open joints. And you can see that, yes, by and large, many of those open joints have, regardless of their mineralogy, do trend to the southeast. But there's a small population, if you look at the very center of that rose diagram with the red color, and that represents carbonate white mica mineralogy. And those actually trend slightly to the northwest. So a slightly different trend than we have with the other open joints. And so again, this is something that isn't obvious if we look at the orientations alone, but adding the mineralogical component tells us, hey, wait, we might have a different set of open joints that are occurring in this deposit. This is an example from a porphyry gold copper deposit. And here we're actually looking at the open fracture orientations. So on the left-hand side, that rose diagram is showing just the orientations with no information about the mineralogy. And in this particular deposit, we see that we have primarily north trending and south trending open fractures. Now, what do open fractures tell us? Well, from an exploration sense, it could be recording the latest stage of alteration fluid or paragenesis in the deposit. And from a ground support and mining side, this is going to give us information about the, again, open fractures are existing defects in the rock. So it's going to tell us about what's lining those defects. And if we have hard minerals lining those defects, they're going to behave very differently than if we have soft minerals that are lining those defects. Okay, so just pieces of information that we can get out of combining this information. So again, if we look at this example, just the orientations alone tell one story. But if we add the component of mineralogy, which is what's on the right-hand side of this slide, this is the mineralogy within the open fractures, we can see that actually montmorillonite, which is of course a very important mineral if we're thinking about our fluid paragenesis, but also if we're thinking about mining, because montmorillonite is a swelling mineral and can wreak havoc in a processing circuit. The montmorillonite is represented in purple here on this rose diagram, and most of the open fractures that have montmorillonite in them actually trend to the south, with very few that are trending to the north. So again, that's a piece that you don't see if you're looking at just the orientations alone. The distribution of the mineralogy within these orientations gives us another key piece of information if we're trying to interpret both the paragenesis of the deposit and the geotechnical perspective of this deposit. Okay, so this is looking at the porphyry gold copper deposit again, except this time we're looking at the mineralogy within 5 millimeters of the open fractures. So on the left-hand side, this is a pole to plane density plot showing just the orientations of those open fractures again. And similar to the rose diagram, we see mostly we have sort of this north and south trending sets. But if we look at the mineralogy within 5 millimeters of the fracture, let's think about what that could mean from a geologic perspective. Well, this is essentially telling us what the wall rock alteration is, right? So it's telling us what alteration we have moving away from our fractures. And if it's different from the mineralogy in the fractures, it could be telling us about what's happening with the fluid. Is it moving through the fractures? Is it permeating into the rock outside of those fractures? All very important pieces of information. So if we look at the mineralogy in that 5 millimeter buffer away from our open fractures, we can see that for the north trending fractures, primarily that 5 millimeter buffer contains kaolinite plus or minus white mica with perhaps a little bit of gypsum. We also see that we, in our south trending fractures, we tend to have gypsum, carbonate, and other minerals that are occurring in that 5 millimeter buffer. So again, this is a picture that without having the mineralogy component, looking at just the orientations alone, we don't get this added piece of information that's telling us again about our fluid pathways, what's happening with our wall rock alteration, but also what sort of minerals do we have lining these defects in our rock. So if we're looking at processing response or mining response, very, very important to know what minerals are sitting outside of those existing defects. So just to wrap things up, there are new developments in the field of structural measurements that are allowing us to measure core morphology and structural features automatically. This includes things like fractures, faults, and veins. And this can provide us with vital information to successfully explore and develop ore deposits, which at the end of the day, that's why we're all here. Structural data is, of course, vital to successful exploration. It helps us map our vein density and distribution, as well as understand fluid pathways, controls on mineralization, and our deposit geometry. Structural data is also fundamental in being able to accurately characterize structural features and is the key to being able to predict the geotechnical behavior of an ore body. And of course, all this information from mining side comes together to guide mine planning decisions and ultimately affects the economics of our ore recovery. The application of automated core imaging technology to both fault, vein, fracture, joint, structural, in general, orientations, combined with the mineralogical component, gives us the opportunity for increased data output. It allows us to target data points and to acquire those data points over shorter timeframes and consistently. So all the data is collected consistently, and any changes that need to be rolled out, whether that be the rotation of an orientation line, whatever it is, all that can be rolled out through the data set consistently. And having the ability to bring all these pieces together means we can achieve robust structural assessment at a number of scales, whether that's deposit scale, regional scale, whatever it is. Using automated imaging systems provides us with a fantastic opportunity to improve our sampling statistics, to provide robust data sets for informed decision-making, while at the same time maximizing value from core that we've already pulled out of the ground and paid for. So we might as well get as much information as we can out of those data sets. And this, of course, leads to better informed geological and engineering decisions. I thank you very much for your time and hope you all enjoy the conference. Thank you.